This program is a presentation of UCTV for educational and non-commercial use only.
Why LED lighting? So basically, LED lighting is basically a solid-state version of a way to create light. So as we know, the solid-state silicon microprocessor revolutionized computing. We wanted to do the same thing with a solid-state, in this case, compound semiconductor, to revolutionize lighting and display. This gives you extremely long lifetimes. Your typical light bulb lasts about 1,000 hours. Our lighting sources can be spec'd out at over 100,000 hours. Very robust, no glass or filaments. Sizes are starting out, we're very small, but now we're scaling them up to very big. They started out at 5 millimeters. Right now on campus, Chancellor Yang has put in about 12 LED streetlights, and UCSB is a member of the LED University Consortium. And these are just past the Henley gate. When you turn right, you can see a very nice white color and save about 40% energy efficiency over the existing high-pressure sodium. Also, they're non-toxic, so this is an advantage compared to CFL. And they're very versatile. They can do a variety of colors, which is now starting to approach very nice saturated colors in LCD backlights and other displays. And finally, they're very cool in terms of temperature. So what is LED lighting? So LED lighting is basically, I like to tell my mother, she asked me what I do, it's a rock that glows when you apply 3 volts to it. So it's literally a single crystal of gallium nitride, and I think Mike Krames will elucidate us a little bit more on the details of the physics here, but basically you combine positive and negative charges to produce blue light, red light, and green light through a very small application of voltage. So I've been working in this field over 20 years, and this is a plot of what's called the luminous efficacy, which is a measure of the efficiency, the light generation efficiency of your light source, as a function of year. And we go back to 1875 to the tungsten light bulb from Thomas Edison, and you can see it's pretty much plateaued out here over the last 100 years at about 15 lumens per watt is the number that I want you to have in your head. So that was pretty much surpassed then by the fluorescent lighting in the 20s, which is now up around 80, 90 lumens per watt, and then metal halide at around 100 lumens per watt, and then some of your street lights, which are yellowish in color, which vary from 125 to about 180. So as you can see, LED technology is this red line here, and when I really started the field in the 80s, it was down around 10 lumens per watt, and then with the advent of gallium nitride in the early 90s, we were able to do about 10 lumen per watt white. So that's where it was about 14 years ago. And today we're up here around 152 lumen per watt. So with pretty much the same chip, you could see we did this 10x that Justin was talking about with this semiconductor too. And we want to go even higher. We predict we can even get up to 300 lumens per watt, but the chart ran out, so I just put a little arrow up there in the right corner. So that's where we want to be actually within a few years. So why is this a big deal, and why do we think it's a large component of the energy picture and improving energy efficiency? Is that this is the site electricity consumption for a large building. 30% of the electricity in any, and this is actually a government building, goes into lighting. So basically what I'm telling you is LED lighting is currently around actually about 50% energy efficient. We could probably get to 90% theoretical, and this is in contrast to incandescent, which is about 4%, or fluorescent, which is up to 25%. This is a large amount of energy. The equivalent is that basically lighting consumes 50% of the energy used to power the cars on American roads today. We could take that number from about 50% of the gas consumption down to about 5 to 10% if you look on it on a purely energy scale. So again, where we are today, we're around 152 lumens per watt. And the way that the white light is generated is we take that solid state blue GaN chip and we pump phosphors, green and red, to generate the 3 primary colors. That's one way to get white light. In the future, another possible way to get even higher efficiency, closer to 300 lumens per watt, is to take a red LED, a green LED, and a blue LED. And we don't know what this material is here yet. Could be gallium arsenide, could be nitride, could be another material. If you did that, then we can even get even higher efficiencies and get higher color rendering. However, this is currently the most expensive solution. So about 90% of the market share is here on the left. You're starting to see some LCD displays that use the 3 chip. So again, if we just looked at your 60 watt light bulb with our current 150 lumen per watt chip, you will save 53 watts if you switch to an LED light bulb. The problem currently is on the market, there's really only a few sources for these LED light bulbs. They're about $60 a lamp is how much they cost. So nobody, in the current thing, the big problem is cost and performance. Nobody's going to pay this $60 per lamp. So we've got to make more innovation, just like Intel did, another 10x innovation on the cost, actually about a 60x innovation on the cost to bring it down to $1 a light bulb. If we did that, then it's a tremendous amount of energy savings. This is a picture of the Earth at night showing you just how much light goes up into space. So this is kind of wasted light anyways, but just shows you the US actually consumes almost 1/4 of the electricity generated on the planet, and a lot of it's on the East Coast here. But if we could replace that lighting with 150 lumen per watt white LED source, it's a huge number. It's about 133 power plants. It's a tremendous opportunity here for energy efficiency to impact the way we use energy. However, there's currently some very big problems here, and I think we'll hear from Bruce Pelton and Michale Krames on the reality is, and this was the reality as about 6 to 9 months ago, it's getting better, is that, you know, people claim 150 lumens per watt. You see this all the time. The problem is it's in little flashlights, and it's done in pulsed measurements, or it's not really done in the fixture. And what happens when people put these up in the ceiling and they get hot is the efficiency drops anywhere from 60 lumens per watt to 30 lumens per watt just by the heating up effect, what's called the thermal load. Companies like Lumiled's Crees have kind of improved on this. I think they can get up to 64 lumens per watt now. So this whole chart has been shifting up rapidly in the last year. So it's very fixture dependent. So I think we'll hear some things from Bruce and Jim Sanfilippo on what's actually out there. The other problem is there's no Energy Star ratings, or the Energy Star ratings are just coming out. So if you buy LEDs, and these are LEDs from 3 different companies located in 3 different countries, and what they're speccing on their spec sheet here is 80 lumens per watt to 50 lumens per watt. But when you actually get the bulb and put it in your fixture at home, you go all the way from what's called a fixture efficiency of 80%, which is pretty good. It means the heat sinking was good and the optics was good, to one of the poorer fixtures, and this was for a downlight for a kitchen, was actually worse than the compact fluorescent. It was 15 lumens per watt. So in other words, you're not saving any money by going to LED if there's no rating. So there's huge challenges ahead in standardization and fixtures. A lot of people are now using the California Lighting Technologies Center at UC Davis to kind of standardize and do these measurements, which are, you know, basically the real applied efficiency. And we see that across the map. But the good news is that if we look at if you design an LED fixture well, which is shown here in yellow here, you can get almost 90% fixture efficiency for well-designed street light fixtures. And I think we're going to have these street light fixtures set up in the tent during the break so you can see just how bright now the LEDs are starting to become. And the good news is for well-designed fixtures, you can get good fixture efficiencies. Compact fluorescent, I might point out, has typically one of the lower fixture efficiencies for the downlight application. It's great if you're going to spread the light everywhere, but for the downlights, which are right above your head right now, compact fluorescent is actually pretty bad. You know, it says 45 lumens per watt, but maybe this is 50 now. It comes out 15 to 20 and is the applied what's on the surface. So there's lots of challenges on the fixture end. Just kind of wanted to point out some of the areas where you may not realize there's LEDs, but your iPhone has LED backlights on it. In fact, everybody's cell phone has LEDs as the backlight. traffic signals were the first thing to go, and Philips LumaLEDs, which formerly was Hewlett-Packard, where I worked, I guess almost 20 years ago, was one of the pioneers in the LED traffic signals. The NASDAQ sign, all the large billboards you've seen are now LED-based. There's some interesting off-grid application of streetlights where they use a big solar panel and a lamp and then a battery in the pole to do basically off-grid street lighting in Japan, and it even has a motion sensor on it. So this is, again, using this kind of idea that Justin talked about intelligent lighting or smart lighting, only turn on the light when you need it. Residential downlighting. And here you see one of the things that a company did to get the high fixture efficiency was put a huge heat sink on it. So that's why it cost $60. And then automotive, we're starting to see LEDs there. Some other architectural lighting. One of the famous ones was the water cube at the Beijing Olympics. Was done with LED lighting. Some bridges. And just this month, Best Buy, I was pleased to see, started using LED. They actually called this an LED TV. It's Samsung's marketing campaign. It's not an LED TV. It's a LCD TV with a LED light in back of it. But that's how they're branding it. And they have a little energy comparison there, and it's about 30% less energy than the current LCD TV. But nevertheless, very nice colors, and it's just hitting mass market this month. And I think Philips and then Sony are following within the next few months. Starting to see it in automobile headlights, however, there's still some challenges here. You have to, I think it was the Audi, you have to actually specify you want LED headlights. And finally, some of the other things that the center does here, we work with Engineers Without Borders, and we have several of our students in the summer go install LED off-grid lighting at certain places like Peru, and then they're going to go to Ghana, I think, this summer, and install basically a solar panel with LEDs to replace kerosene lighting, because actually lighting by kerosene is the most inefficient lighting source. It's about 0.3 lumens per watt. So we're talking about almost a 10,000-fold improvement over kerosene-based lighting with these systems. So this can really impact almost half the world's population uses either fire or kerosene. So in conclusion, you can see the R&D is looking really good for small chips. However, cost is a huge factor, and actual applied fixture efficiencies are much lower due to some of the reasons we're going to hear about from our next speakers, which will tell us where the current status is, where they see the future of it, and what's the existing problems we can solve. So we've invited Michale Krames here from Philips LumaLEDs, Bruce Pelton, Director of Engineering at California Lighting Technology Center, and then an entrepreneur, Jim Sanfilippo, who's going to tell us how he's using LED lighting in the Hollywood studios. So without further ado, I'd like to invite Michale Krames up. Thanks.
LED fabrication very much follows the same processes, very similar processes as are used in the silicon industry, which is a very good thing. If you look at what's happened for silicon-based devices in terms of the efficiency, the capability, power handling capability, and the cost, those have all gone in the right direction, and that's what's allowed companies like Intel to do amazing things with the technology. And a lot of the basic processes that we plan to follow with 3.5 technology, so compound semiconductors, are the same way. We use, we take bulk substrate materials, we deposit by various epitaxial techniques, layer structures. Here we do standard wafer metallization, wafer fabrication, dicing, and packaging of these devices, just as what is done in the silicon industry. And so we can leverage a lot of that. Still have a ways to go, but we have a good track record in front of us. I mentioned before the lifetime or the history of the LED. So Nick Holoniak's first visible spectrum LED was 1962 in GE Research Labs, and that led to the first commercial products. They really began to take off in the late 1960s and early 1970s as indicators for calculators, watches, and things of that nature. And gradually, each of these material systems, which I won't go into, but they basically improved. So people were looking at different alloys of column 3 and column 5 materials and seeing what their materials properties would be and seeing how their light generation efficacy could improve. So the scale here is lumens per watt. Steve threw out a number 15 lumens per watt for an incandescent bulb. That's a number to remember. Another thing to keep in mind is that there's a theoretical limit. A lumen is a register of how well your eye sees light, of any white light spectrum between 300 and 400 lumen per watt. And the reason that there's a range there is that for broad spectrum like daylight or incandescence, these are broad spectra. They tend to have a maximum luminous efficacy of about 300 lumens per watt. If you allow your spectra to be more spiky, spikes in the blue, red, and green, you can get that up to 400 lumens per watt. So that's the range there, and it's a number to remember because you can't ever do better than that. And so if you look at a ratio with respect to that, you can kind of see where you are in terms of total efficiency. Most of these points here are in the red, and these are red LEDs or orange LEDs and maybe some in the amber. In the late 80s and early 90s, the gallium nitride-based materials were basically developed to I would say, a modern era by several key inventions in Japan, and also in particular Tsuji Nakamura, who's now here at Santa Barbara, pushing this technology to where it was inevitable to go. And based on that material, the blue devices are now used to pump phosphors. I'll talk a little bit about that, with the best devices now up around 169 lumens per watt. And that's for a spectrum that's probably about 330, 340 lumens per watt. So that's 50% efficient, which is a really good number, but there's even more to go. To give you a little bit of flavor of the kinds of things that people do, in the early days, when we had indicator LEDs, we just had to have them bright enough to see it. And there wasn't a lot of motivation to improve the efficacy anymore. So what people did is they typically worked on cost. So simplified processing, how can we scale up the wafers and make the devices as cheap as possible. In the mid-1990s, when we started to have efficacy levels that were comparable to conventional lighting, and when we had the white LEDs, the whole game changed. And this is when you saw a lot of the big players in lighting, Philips included, really get involved to say, hey, this is going to be something big and let's do something about it. So Philips contacted Hewlett-Packard in the mid-1990s and formed a joint venture shortly thereafter in 1996 called Lumileds, and that's basically now has been bought back into Philips, and we're Philips Lumileds at this point. The same thing has happened also with the other big companies like Osram and others. But a major breakthrough then was in this mindset, this way of thinking was, okay, let's improve the devices to their maximum theoretical limit. And what this chart shows here is the light extraction efficiency. So this is the fraction of light that one is able to extract out of an LED chip compared to what's generated within the chip. And there was I can tell you in the mid-1990s, there was a feeling, well, 30 to 50% might be as much as we're going to get out of these very high refractive index materials because of metals and losses and things, and the fact that they're very high refractive index materials. But in fact, we have with the newest technologies, and ours is called thin film flip chip, other companies have others, by really working on optimizing the structure, reducing loss, and maximizing light output, we're able to get 80% of the light out of the chip into the useful ambient, which is the package with the silicone. That shows a picture of such a device. It looks very similar to an efficient solar cell design, and there's a reason for that, because we're doing basically the inverse problem as the solar cells. So we want to minimize loss, generate light as much as we can everywhere very efficiently, and take it out of the device. There's a cross-section here. The external efficiencies are a product of that term I just talked about, extraction efficiency, and the internal efficiency, which is how much of the current that we put into the diode is actually generating light inside the chip. So it's that product of those two quantities determines the external efficiency. And the peak external efficiencies at low currents for a device is over 60%. So by that, you know that roughly 80% of the current is turned into light, and then 80% of that light is extracted from the chip. And that's where we basically are today. There is a roll-off in that performance as a function of current, and I won't go into that, but that's an area of opportunity for improvement. So if you look at a summary of the LED performance as a function of wavelength, in the two material systems, this is indium gallium nitride for the blue to the green, and an Allen gap material system for the red to the amber, you have a situation like this. It's a little bit cruel of Mother Nature that this is an eye response curve, so your eye is most sensitive at 555 nanometers, and that's exactly where we don't have an LED. So if you have a good idea, come talk to me. We'll figure out what we can do with that. But the good news is that we can really make use of these blue LEDs because we can use down conversion to make white light. So there's two ways. Steve mentioned a multi-primary mixing. If you have very efficient red, green, and blue emitters, you can do very well with a multi-primary mixing. But the vast majority of white light today is used using down conversion, just for the reason I just described, is that there's not a really good emitter in the green. So we basically apply phosphor powders. There's other forms of phosphors like phosphor ceramics we can put right on the LED chip and convert some or all of the blue light into the colors that we want to make white light. This just shows an example of that. So we have here a blue LED that is fractionally converted into a yellow phosphor. This is a garnet phosphor. We call it YAG. It's a cerium activated phosphor that has a yellow spectrum. And by balancing out the amount of blue light and the yellow light, you can traverse in XY space the black body locus and hit it at the right point to make white light. And this is how the vast majority of white light LEDs are made today by this process. Single yellow phosphor on a blue LED. And at the efficiency levels for the blue LED I described before, the performance levels are above 100 lumens per watt. And you can buy those now. There's commercially available products. In fact, we even have products now that are they're minimum rated 4 lumens per watt. So you can buy the LED and you know it's going to be at least 100 lumens per watt. Back in terms of efficiency, that's about 30% efficient, 33% efficient. And again, this is at the LED level 1. And if we track that now as a function of time, Steve showed a similar slide compared to halogen, incandescent, fluorescent, and metal halide. You can just get a sense here now on a linear scale how fast this technology is moving. And the momentum behind this is enormous. And the expectation is that we will leverage this. We're on track to meet this DOE roadmap. Right now, it's going to get real hard when we get up here, so we'll see what happens. But the momentum behind this technology is huge, and it's going to continue to push. The spectrum that I described before with a single yellow phosphor provides a cool white. It's useful for bicycle lights, portable lights, even some outdoor illumination applications, but it's really not something you'd like to have here or indoor. We really need a warmer spectra in order to do that, something that mimics an incandescent bulb. And that's shown here. This is, again, wavelength. This is a black body radiator at 3,300 Kelvin, so that temperature is close to what you have for a halogen, like an MR16 halogen you might have in your house or store. And it's important there that in addition to the yellow phosphor or green phosphor we add a red component to flesh out that spectrum. We have a little bit of a gap here in the cyan, but we can match the black body spectrum fairly well, so the color rendering index can be very high. I won't go into what that is, but 100 is the best you can get, and only incandescent bulbs get 100. For most indoor applications, low 80s plus are good enough. 90s are even considered deluxe lighting. Most fluorescent lamps have CRI indices of around 83, and in offices they can be even less than that. The important thing is the color temperature is what people are used to seeing as warm as light indoor in homes. We do pay an efficiency penalty for that. So in addition to the fixture effects that Steve talked about before, there's also this thing in the industry where when you hear about very efficient numbers reported, these are often for these cool white LEDs, which are not necessarily the ones you would use for illumination. It's really the warm white LEDs, and we do pay a penalty for that. And part of that's fundamental because we're generating a lot of red photons, and that's a lossier process in generating yellow photons. Nevertheless, the gap there between warm white and cool white is closing, and the warm white devices are improving rapidly. So what can we do with this technology? The vision we have is that there are multiple sectors that we can go at for lighting. So in addition just to the raw performance and energy efficiency possibilities, there's also all kinds of possibilities in dynamic control of ambience, human factors effects, the things that can improve people's quality of life or the perception of their surroundings and environment. I don't have time to go into all of that. But what I will do is focus on the lowest leftmost corner here, where in the retrofit area, we see already an opportunity to bring solutions to the table to the consumer that are going to improve energy efficiency. And so if we look at the LED adoption today, initially we have the applications where there's a huge value proposition. For example, refrigeration. Fluorescent lamps don't like to be cold. They're very inefficient. And so there's a huge programs now. Walmart, Tesco in the UK completely get rid of fluorescent lamps and replace them with LEDs. The energy, there's a lot of energy consumption in these refrigerators and freezers that they use, and the LED solution is much, much better. Lighting in difficult to access locations, so where maintenance costs are very high, LED solutions are great. Portable lighting obviously is great for LEDs, low voltage and everything. The next area of opportunity is where total cost of ownership makes sense. For example, a very good example is road lighting or street lighting. Maintenance costs for road lighting out on a highway are enormous. You have to get a truck out there, shut down the highway, and get somebody up there to dismantle and replace these bulbs. The other nice thing about LEDs is because they're a very small source, it's easy to put light where you want it. And that's not true, for example, low pressure sodium, which is very popular in the Bay Area where we're located. These yellow lamps are gigantic. And it's not cost effective to put an optic around this thing to put the light where you want it. So there's all kinds of light pollution and a difficulty to illuminate the street the way you want. And that utilization efficiency can be like a factor of 2. So in addition to the very good efficacy levels we're getting with the LEDs, there's like a factor of 2 benefit one can have by just putting the light where you want it and reducing light pollution. So we're seeing a huge uptake right now in outdoor lighting and LEDs for road lighting. And this is, again, just another example of how things are going to take off. How do we get to the, this is just the refrigeration lighting, I'll skip through this for time. How do we get to the end consumer though? Again, back to the Home Depot scenario. We need to get these products out into people's hands. And the fastest way to do that is to put them into retrofit modules that they know and they understand. That screw into existing sockets. I'm not saying this is the most elegant solution. There's a lot more we could do with LEDs. This, in a way, is not taking advantage of everything we have with LEDs, but it is offering improvements in energy efficiency and getting them in the hands of consumers that are going to know how to use them. So the selling points here, these are some retrofit lamps. These will be available in the US as early as September this year in stores like Home Depot. These are Philips products and rated in all the ways that we make sure in terms of lifetime and so forth. The energy savings can be very large, especially in the case of these spot lamps. This is an R20 bulb. This bulb puts out the same beam pattern as a 35-watt halogen, and we use only 7 watts of light to do that. So part of that is in the efficacy of the LED, but part of it is also in this light utilization thing that I was mentioning before. There's no ultraviolet or infrared radiation in the beam. That can be a big deal for applications like museums where you have materials that are very delicate and can be destroyed or damaged by UV light or by heat, and that more or less comes for free, so we call it a cool beam. The lifetime is there and less maintenance costs because of that. So in hotels, for example, you don't want to change all your retrofit sockets. You leave those in there, you put these in there, but now your relamp rate comes down dramatically. So there's cost benefits there. Why LEDs versus compact fluorescent? Compact fluorescent is more efficient than incandescent technology, but the LEDs are really coming on strong, and the competition is going to get pretty severe. Certainly in spot applications, LEDs are hands down the winner because of the source size. The nice thing also about LEDs is we don't have to worry about mercury. And I will also argue that in the future we'll have less electronic waste fundamentally than compact fluorescent. And if you want to talk about that, we can talk about that in a break. It's a bit of a story. But there's a real opportunity for LEDs not only to displace incandescents, but also to compete very heavily with compact fluorescent and in my belief, take over all those applications as well. Just a couple more products that will be coming out. So there are MR16 replacements that you'll see. Even candle bulbs that you see in chandeliers. There was a question about how are we going to make a candle bulb out of an LED, and it has to do with working on the driver technology and actually getting rid of the driver and having the LED do part of your work. So again, this is really trying to mimic what's out there. But there's a funny story. The original bulb made by Edison was actually designed to kind of mimic a gas burner lamp back in the 1890s, and we're doing the same thing now. So a little bit monkey see, monkey do. Also higher power lamps, par 38s, downlighters, and this is a case where Steve rightly pointed out, we talk about LED efficacy, that is not necessarily a system efficacy. And you can have compact fluorescents that are 50 lumens per watt, and you put them in a fixture like here, and they're 15 lumens per watt. So we're all very conscious of that. We have the Energy Star ratings that DOE is pushing are going to help with this sort of thing. There's other rating programs that are going to help with this sort of thing. And the industry is aware of this. And a good example is this Fortimo module. This is a downlight module, and the system efficacy of this module is 62 lumens per watt in warm white. And this has to do with just engineering everything, engineering the optics, engineering the driver efficiency to make sure that we keep as high as possible. With all that said, the costs are very high, and we have to reduce that by factors of at least 20, if not more, 10 to 50 times. How can we do that? Just real quickly, we have an opportunity to increase the power density that we use the LEDs at. They're driven at fairly mild current densities right now. We have an opportunity to increase that by a factor of 5. We have the opportunity to improve the efficacy of a warm white LED by a factor of 2, easily, I mean certainly doably. That's a factor of 10 right there, just in the performance of the device. And there's easily a factor of 2, if not more, much more in terms of the manufacturing, scaling up to larger area wafers, doing better on the processing, smarter package design and all that sort of thing. So factors of 20 are going to happen. And so these $60 type bulbs that we talked about in the past are going to come down to be on the order of a few dollars. If you throw in some rebate programs, that is going to help this thing get over the fence and get to the consumer. So I think I'm running out of time. I will just mention that briefly, that certainly in the EU, the ban on incandescents is there. It's happening. It's very reasonably aggressive. It could be more aggressive, but it's reasonably aggressive. This kind of thing is really going to push the technology forward for general lighting. We are sensitive to the quality issues that plagued compact fluorescent for many years. It took compact fluorescent 30 years to really get mainstream in the market, and a large part of that was the early products that came out the door were extremely inefficient and had poor light quality and also reliability issues. The DOE is sponsoring an SSL Quality Advocates program that we endorse here to make sure that solid-state lighting products meet certain standards, and this is going to help. And I think I'm out of time, so with that, I'll end it and take questions. Thanks.
Thanks very much for having me. It's great to be here with the IEE. It's great to see Jeff Henley. I reminded him that 35 years ago, we were battling to start the first energy efficiency department in a Fortune 500 corporation. And I had to bend his arm to buy a computer for the department, and now he buys a whole company. At the CLTC, we were founded 5 years ago by the Department of Energy, the university, the California Energy Commission, and the National Electrical Manufacturers Association. We have as active members of our center the major utilities in the state of California. And you'll see here represented about 75% of the volume of the U.S. lighting industry, who are also members of our center. A great number of those are already operating in the LED space. At the center, we are fairly source agnostic. We think it's important to move things forward, the most efficient source for the application at the time. It's a moving target, but we want to explore here a couple of the sources and that are best, we feel, for the applications. This is kind of busy and will be in your materials, but it shows that very much what Steve said. LED system lumens per watt cost is about 6 cents a lumen. The existing sources are somewhere between 3/10 and 8/10 of a cent per system lumen. So there's still a while with LEDs. That being said, Haight's law says that we're going to move very quickly. We have a rapidly diverging line on the output and a rapidly decreasing line on the cost. So the chances are we're going to close this gap very quickly, probably within the next 4 or 5 years. When we look at technologies, again, for office ambient lighting, and we work very hard on a task ambient model where there is general lighting across the area and then specific lighting where it's required. In that case, fluorescent works very well. Again, it's a cost of 3/10 of a cent per system lumen, low glare, and it's eminently controllable to respond to demand situations, to daylight harvesting and the like. It's a very good area source. In the garage situation, low bay induction lights look very promising. They promise source life of 100,000 hours and low cost. And again, they're an area source. We're able to go ahead and to drag those down to 25 or 35% of total output when the occupancy is low. In high bay situations, in warehouses and in retail, there's a requirement for some uplight to help expose the superstructure of the building and not make it look like a cave. In this case, metal halide works very well. New ceramic metal halide technologies are running 120 to 140 lumens per watt. Once again, they are controllable and can respond to demand response, to daylight harvesting, and to occupancy. In the sports lighting arena, we're looking towards now the application of plasma induction lighting. Plasma induction lights are made with a capsule the size of a Tic Tac breath mint, but put out 22,000 lumens at 140 lumens per watt. The exciting thing about them is the color gamut. Here's a typical gamut as you've seen for LEDs, and it peaks a couple of points along the way. The gamut now for plasma induction lighting is practically level. It illuminates all colors well. It is a type of lighting that we really haven't experienced, but as you see it, it's very much appreciated. It's actually superior to black body radiation. In parking areas, we've moved rapidly towards LEDs. This is an installation at UC Davis where we're changing out about 4,000 fixtures. We're doing that now also here on the campus UCSB and on the campus UC Irvine. There's a commitment now across the UC system and the CCC systems to reduce energy consumption by 50% in the next 10 years. And this will be a large part of that. Each of these fixtures has occupancy detection built in. So when no one's there, the garage lighting goes down to a very low level. When someone walks up or drives up, it jumps back up. You can see this now compared to the yellow lights that Michael talked about. By controlling them and by having more efficient distribution, we've been showing a consistent 68% reduction in energy consumption. For task lighting, LEDs are perfect. Putting them close to the desk gives a very high contrast light that does a very good job on the paper task that we still have in our electronic offices. They also take advantage of inverse square law. When we're lighting from 1 foot instead of from 5 feet away from the surface, we're able to do it with 4 times less energy from the very beginning. So it works very well. People can move those around, control their own workspace. These also are equipped with an occupancy detector. When they walk away from their desk, the lights go off. Also, as mentioned, in refrigeration cases, they're perfect. LEDs hate heat, so do refrigerators. It's a good pairing, and they work very well. Once again, they too are controllable so that the aisle is somewhat illuminated, and then as people approach the refrigeration case, it jumps up to full brightness. In downlight applications, we've seen great success. Again, because an LED is a directed source, it works very well for this kind of application. Once again, it gives great dimmability. Unlike compact fluorescent and other sources that tend to shift color, it maintains color consistency down to a very low level and can run as low as 0.5%. There are a number of issues that we're going to have to tackle together with the pricing issues. When we go to convert conventional luminaires to LED, we have to deal with a thermal situation. This is a line of products that's being made by the largest supplier of lighting products for the residential market. And we've had to take what used to be light metal spinnings and make those into large metallic heat sinks and hide them in the old form factor. This is the new generation of restroom fan, and it has also built in a nightlight component that's at a low color temperature. For downlight applications, again, you saw the large heat sink. Also, to mimic existing sources, you'll see that they're mixing amber, red, and white LEDs to warm the beam up. So we have to deal with heat sinks. We have to deal with optical situations. So creating fixtures is not a matter of just converting fixtures. For the refrigeration cases and all the other uses, LEDs, again, are forward. When we have a situation where we want to go sideways, we have to enhance their output with specialized optics and go ahead and move it sideways in the case to try to provide even illumination across the face. We have a real issue with glare on LEDs. The source is the size of a grain of sand. With all that illuminance in that smallest space, it dazzles the eye. We're finally getting to the point now where LEDs are efficient enough that we can turn them upside down and then drive them indirectly down and blend that light together. That proves to be real effective. And finally, now we're at a level of efficacy where we can take the loss that that engenders. There's an issue with color binning. Michael talked a little bit about consistency with the black body locus. The difficulty now is that most manufacturers have to buy within 4 bin groups to be able to buy affordable units. That means across the bins, there's a broad divergence of color appearance. So this is an area where we're going to have to work to get that more narrow. Additionally, with LEDs, we have to deal with issues about CRI. CRI, as Michael measured, is 100% for incandescent. It was determined by using pastel color swatches that were illuminated by a black body source. When you're not trying to illuminate with tungsten anymore, it doesn't look right. You cannot use the same metric that you use for burning tungsten for a solid state source. The National Institute of Standards and Technologies has come up with a new standard, and it's called Color Quality Standard. It uses real colors from the real world and measures the source on how well it renders the physical colors. Additionally, with LEDs, we have to deal with hue and saturation and luminance. We have many more factors that the human eye can see that never came into play with conventional sources. We have an issue with electronics. The source we're confident will last 60 to 100,000 hours. But when we drive with an electronic driver that has as a key component an electrolytic cap that's rated at 3,000 hours, we have a disconnect. So if the system cost benefit is based on the longevity, we have to make sure that the electronics are going to last as long as the sources. Likewise with the optics. If the optics begin to yellow and begin to get clouded, it doesn't matter if the source goes on for 100,000 hours. The fixture is no longer useful. Also, we have the problems of nature. Bugs like well-lit, warm places, like light fixtures. When you have a conventional source, you have to open it up to change the lamp, and hopefully you'll shake the bodies out of the fixture when you do that. If we have an LED rated at 60,000 hours, that's 15 years of burning every night. That's going to be a lot of accumulation of bugs. And then when the birds like to go and build their nests on top of the heat sink, we've got another problem. So all of that great design can go right up in fur and feathers. So we're working on designing fixtures that properly integrate LEDs, This is a ceiling fan that operates on about 28 watts of lighting and provides much more light than the 150 watts worth of incandescent. But you can see that we've had to do some tricks with heat sink and so on and hide it inside the fixture to make it aesthetically acceptable. Manufacturers are very good at screwing together things, bending metal, and painting it. We show them LEDs and they say, that's really neat. Now, how do I screw it down? We've got a problem. They need a little training. Likewise, the designers have got to learn how to deal with the task ambient model. If they try to use an LED to broadly light an entire area, it's a problem. There's going to be scads of them all through the ceiling. So we're working with them now to train them in using LED technology. Finally, the installers have to learn to install intelligent technologies. DOE had the smart thermostat years ago, and they found out the smart thermostat used 40% more energy than a regular one because no one could operate it and no one could install it. So now we're training the electrical contractors. We've begun to train in Southern California now. Next year, we'll train some 8,000 electricians to install controls, lighting controls, and intelligent technologies. The last point I'd like to make is one about not repeating the sins of the past. We've talked a lot about compact fluorescent today. It's been 30 years. 30 years out, we're all at 21% penetration in California with the greatest acceptance of CFLs. A lot of that happened because they were overspecified, overhyped, and underperformed. We see a lot of LED products now that are trying to mimic conventional sources, and they don't do it successfully. If we continue to allow this and to see this, the consumers are going to vote away from using LEDs. We think LEDs have a bright future when they're properly applied. We think that they're going to supplant conventional sources within the next 5 to 7 years. Thank you.
And my background is a lighting designer. I've been lighting motion pictures and televisions for the last 21 years, and I got very frustrated with the technology that's out there. And so I decided to do something a little different. This is a product that we're shipping now. We started, our first customer was the new James Bond movie. I'm going to turn this thing on. This is our new product. It's a little lithium-ion battery pack. It'll run this light for about 30 minutes. Essentially what you're seeing here is LumaLED's technology, actually. We're actually using some other people as well. But this is about 2-year-old LEDs. They've been on the market for long enough for us to utilize them. This particular fixture has interchangeable lenses, so I can change the beam angle on this to make it more useful for our customers. So we can, not as directed a source. We've got an integrated power supply and dimmer control built in here. They were kind enough to give us the best new product of the year at the LDI convention, which is a convention mostly about entertainment lighting, live event sort of things. And we've been able to get some really good feedback customer-wise from our first primary customers. Our first customer was the new James Bond movie, Quantum of Solace, that's come and gone from theaters. They wanted to use this light mostly because of the durability side of it. They really didn't care about the energy efficiency side of it. You can drop this thing off a ladder and it's still going to work. That's why they wanted to use it. They wanted to use it on the car rigs. There's a lot of car chases in a James Bond movie, as everyone knows. They beat the lights up pretty bad in those situations, and they liked the fact that they weren't going to be able to break this fixture. It also allowed them to do something they've never been able to do before. They took 5 of these lights and strung them together because they're a stackable modular system. They used those on the back of a motorcycle, powered it off the battery of the motorcycle, and used it as a mobile light stand during the initial car chase sequence that starts the movie out. It gave them the capability to do something they've never been able to do before, and it's all because of the robust nature of solid-state lighting. It also gave them a little bit different approach. This rig was, again, from James Bond. It was towed in this configuration. The rail that's holding the light on the one side, they would mount the camera on the other side, and it became a free driving vehicle, so the actors would actually drive it. They wouldn't have to add a generator or extra battery packs. They literally inverter on the battery on the vehicle and drove off. That side of the energy efficiency was very interesting to them. The low heat side became very interesting when they were dealing with actors like Judi Dench. There's a scene in the movie where Judi Dench is in a bathroom. It was a very tight set that they shot in London, and it happened to be a very hot day that they were shooting. So they brought in our fixtures to not add any heat load in that small space, because Judi needs a little bit more makeup than some of the younger actors out there. CNN used our products at the Democratic and Republican conventions. They were definitely interested in energy efficiency, not for the same reasons that everyone thinks. They pay a premium for the electricity at venues like this. Normally they would ask for 3-phase 100-amp service for their skyboxes at a venue like this. They asked for 60-amp 3-phase. That saved them $3,000 a venue for the cost of the power. It paid for the rental of all the fixtures. They were really happy, and it turns out that they were so happy that they used them again during the inauguration. And they're thinking about using them some more. Because of our connections in Hollywood, we're able to get some decent talent to use our fixtures. This was a YouTube video that Leonardo DiCaprio produced called Don't Vote. And so it's always good to get pictures of Steven Spielberg standing next to your product. Helps in the sale of things. Oprah was kind enough, let's see if this launches or not. Oprah used our products at the inauguration, and I don't know if this video is going to run or not. Maybe not. Oprah used our stuff at the inauguration mostly because they couldn't get a permit for a generator to put on the street outside the restaurant that they wanted to film at. One of her ex-chefs opened a restaurant in DC. It was very close to the parade route. They couldn't get the permit for the generator. So they needed to use, the house power, the power available at the site. They had 40 of our fixtures that illuminated the Oprah and her 4 guests, as well as all the audience members, which were the table seated behind them. They had 40 fixtures. They used 2 20-amp circuits to do that. This particular fixture uses around 65 watts of power, and it's putting out about 300 watts equivalent. The video that I like to show, the roof is very low, so you can see all our fixtures and all the wide shots of the thing, so it's great for us. These are some of the other motion pictures that have used our fixtures, and it's hopefully more coming. We've got a next generation product coming out. We call it the SL. Stands for Space Light. A space light in the movie industry is a 6,000 watt fixture, tungsten halogen. It uses 6,000 watt globes. Because of the orientation of the globes cook themselves, and they last about 100 hours or less. And then they have a tendency to break and rain down hot glass over the set. It was more of a safety issue. So the maintenance side of dealing with these fixtures is a big issue for the studios. And so if you start to add in the electric use of the lamp, the electric use of the air conditioning load that's being generated by tungsten halogen in the space, and the maintenance costs, it's very expensive to operate these things. The example that I like to use is the ER hospital set. They had 70 of these 6,000 watts fixtures that were over that set. The reason I have this photo is that light that looks like a fluorescent bay, let's see if the laser works, this light source here is actually 2 6,000 watt space lights that are over a diffuse frame. They take the frame off many times when it's not in shot so they can get more illumination where they need it. Once a week, there's 2 electricians, union electricians, that get to go around and replace all of the light bulbs and all of those fixtures so they don't fail during the, filming. It's a big expense. Warner Brothers asked us to build this fixture. Our first demonstration, it was around a 700 watt, and we were getting almost the exact same quality and quantity of light out of the fixture. We're going to hopefully get this released by the end of the year. And you know, Warner Brothers, Paramount, and Sony are all sort of standing in line waiting to get this purchased so we can get it out there. And so taking the technology that's being developed by, you know, the CLTC and Lumileds and other companies, and taking that to, you know, commercialization is really what we're focusing on. Getting that from, you know, A to B is sometimes a long process. The LEDs that we're using in the space light have only been available on the market for about 8 months, and it'll be the first commercial fixture out there. It's not going to be cheap, but luckily the movie industry can afford some of that. And because of the energy savings and the maintenance savings and, you know, numbers, you know, when you look at total operating cost over the fixture life, that's a big number. You're almost paying $40,000 to operate a fixture, and you haven't even paid for the fixture yet. Right? That's over the course of 15 years for this particular number, but it's pretty compelling when you look at it in even a short run of a motion picture where they might have a setup for a month or two. I don't know if any of you saw the Pirates of the Caribbean movie, the last one. There was 2 ships, sailing ships, fighting each other in a space. A friend of mine was the gaffer on that project. He used 1,300 6K space lights to be the base ambient level over that set. They shot in that set for 2 months, and the rigging of it was a month prior, and D-rig was a month after that. He had a crew of 6 guys every night come in and replace burnout bulbs. That was all they did all night long. So they brought in a structural engineer to sign off on the cable load for all the wire that they had to put in the ceiling, because all of these lights were wired back to dimmers on the floor so they could turn them on and off without having to you know, have the extra heat load in the space. So it's a big problem when we're trying to address the big sort of, you know, market that Hollywood is, and most people don't realize sort of the energy use that Hollywood consumes. On any given day in Hollywood, if we were able to replace just the space lights in use and the fixtures of that size, we could essentially turn off 2 coal-fired power plants. And that's the goal. So there was another video there that was going to be my closer, but it's okay. I'll take your questions at this point, and hopefully we'll get caught up on time.